Hello, everybody. Thank you very much for showing up and waking up so early and coming to my workshop. My name is Peter Mindek. I'm from Nanographics, and this is Making Music with Math. So let's start with some basics about sound. Sound is a wave. You probably heard that, right? What it actually means is that when there is some object in air and it vibrates, it starts moving starts moving air around. So here we see some air particles and some things. We make it vibrate, and then we'll be pushing these air particles away and sucking them back. You know, air is elastic, so when you push it away, then it comes back afterwards. We can make a little bit more of these particles so you can see better how these waves actually look like. So sound waves are lateral waves, which means they move in the direction, or they oscillate in the direction as they are traveling. You know, so unlike light, which goes like this, the air goes back and forth. We can highlight some of the air particles so you can see what they are actually doing. So notice any single one particle, right? It goes back and forth, away from and back to this sound source that we have there. So they don't go anywhere, right? So sound isn't like some particles, you know, going from the sound source to your ear. They stay at the place, right? What moves is the wave. It propagates. You can notice here in a corner, I put a little scale so you can imagine how fast sound goes. So this is how much sound goes in 1 second. It's 340 meters. Or if you want, 3 football fields. So that's just for your kind of imagination how fast sound goes. It's much slower than light, of course, but it's still pretty quick. So now, you often, we talk about sound and you often see sound. I also put this little sound wave at the beginning. So what does it mean? And how do we actually hear? So what our ears are doing, they're detecting air pressure. So here, I mean, you can see the pressure because I made these particles with additive blending, right? So if you see more of them, it's brighter. If you see less of them, it's less bright. So when it's bright, there's a higher air pressure, right? So what our ears are doing, or microphones are doing, in one point, they are measuring essentially the air pressure, right? So we could put a measurement tool there, and this is the current air pressure in that very spot, right? And what we can do, simply we can plot this value over time. And that's those sound waves that you see, all the visualization, whatever. So these are basically plots of this air pressure over time. As I said, the sound waves, they are lateral, so they don't actually look like this, right? It's just much easier to understand the waves if they are plotted as if they are going perpendicular. So we will be using this kind of plot a lot in this seminar or in this workshop. So just for what does it mean if it's like that? Another thing, so this is how it usually looks like, right? I can play something, and then you can see these waves over there. This is basically a short window. In this case, it's 10 milliseconds of the sound that you currently hear, right? Another way to look at sound, though, is through the frequency domain. So this is a time domain. It means that you can see how some value changes over time. But what you can also take a look at is are the frequencies that are in the sound. So you might have heard that sound has many frequencies in it. What does it mean is that, well, there are two concepts that are kind of in play here. One is the way how we physically hear things. Our ears, they don't care about this time, signal. They actually detect different frequencies. You have different cells in your ears, which have little hair on them, and these hair are kind of waving, sending signals to your brain. And each cell has different frequency that it can pick up. And also, another thing is that there is this thing where any time signal can be represented by a series of sine waves, which is this Fourier transform thing. And that is what we are actually seeing here. When we do a Fourier transform of this signal, we will see these frequencies over here. So, and you can also do the inverse Fourier transform to go back. So this is a simple way how to switch between these two domains and then you can visualize them, look at the sound. You know, so if I, let's make a sine wave. You know, it's not so easy. It's kind of sine wave, right? Okay. Here we go. It's still not a sine wave. What's going on here? Let's call it good enough. No, it's not good enough, seriously. Yeah, there we go. So here we see a sine wave, and here you see the power spectrum of it, or you know, like different frequencies on one axis and how loud they are on the other axis. If I play a sine wave, it's just one, right? If I play two of them, you see two of them, right? So this is what it basically means. We'll be also looking at the other plot a lot. By the way, you can stop me anytime. If anything isn't clear, please stop me, ask me a question, so that you know we can all progress. You know, that everybody understands everything. Anyway, so with that done, let's take a look at sound. Let's start like this. So as I mentioned, these different frequencies, they're all sine waves. You know, so you can take a bunch of sine waves, put them together, and you have any sound that you wish. But let's first take a look at a single sine wave. It has several properties. I mean, this is very basic stuff, right? You probably all know that, but it's always kind of good to see that in relation to sound. So this is a like simple formula which kind of generates this sine wave, and we can use such a formula to generate sound as well. We just have to use the frequency of it, which is this f over here, high enough that we can hear it. We can hear all the frequencies from 20 to 20,000 hertz. And hertz means that the sine wave goes up and down several times a second, you know? So if it's 1 hertz, it's go up and down. It has one period in 1 second, right? Then you have like an amplitude of it, which is how high it is, and that's what we perceive as volume. The higher amplitude, the louder it will sound. Here, the amplitude is basically you just multiply the sine wave with some constant, right, or some number. So here you can see what you change by changing the A, right? This is what you change by changing the F. That's the frequency, right? So if you do it more often, you know, you will have higher frequency, and also your sine wave will look more squished. And the last thing, which is also kind of interesting, is phase. A phase, it's, you know, you just add some constant into the sinus, and that's where the sine will start. So these are the three properties we kind of, you know, have, and we can change them. We can change them also over time, and this is called modulation. Modulation is very important for synthesis, and it means that you modify a signal by some other signal. Modify, I mean multiply, you know? So here we have some examples. When we modulate the amplitude, for instance, let's say here it's constant, it's 0.3. You see my mouse? Yes, you do. And here it's, let's say, 1, and in between it just like, you know, gradually changes. So this is what would happen to your sine wave, right? With a frequency modulation, also very kind of intuitive, right? You know, you have lower frequency, let's say 700 hertz or something, then you have 1,600, and in between it gradually changes. So this is what would happen to your sine wave. Now the phase is kind of weird. You know, let's say we have phase 0 here, phase 10 here, and here in between these two lines it gradually changes. And it looks like it changed the frequency. You know, that's kind of weird, right? We can also revert it. Let's take a look at the other, you know, the other way around. So with amplitude, it's, yeah, clear, right? You have a sine wave and then gradually gets smaller. With a frequency, the same. It's kind of squished and then gradually gets wider. And with a phase, again, it's weird, right? Like phase here is 0, here is -4. You know, the sine wave looks the same because we just shift it. But while we are shifting it over here, the frequency seems to be lower, right? We can actually take a look here and hear how it sounds, right? So that's the sine wave. It doesn't do anything. It doesn't do anything. Okay, so it's very silent sine wave, but you can hear it, kind of, right? And when we modulate the amplitude, see what's happening? That makes sense, right? Now, if we modulate the frequency, that's what happens, right? Also kind of intuitive. Now, what happens if I modulate the phase? weird, right? It sounds like modulating the frequency. But yeah, think of it in these terms, right? The phase is basically just the position of a sine wave, and we are kind of going through the sine wave, and if I'm moving the phase while it's going on a sine wave, it just goes faster, which means the frequency is higher. So if I change the phase up, the frequency will go up. If I change the phase back, the frequency will go down. So essentially, for our purposes, frequency modulation and phase modulation are essentially the same thing if you're modulating with like a sine wave, you know? And that's also important, and it will be important later. Anyway, just one thing that I also want to kind of define this term of harmonic, because we will be talking about that a lot. So just so you understand, this is a sine wave, and it has some frequency. Harmonics are sine waves which have integer multiples of that frequency. So here we see like a first harmonic, it has, you know, or you know, this is, let's say, 0. No, this is first. First harmonic is the wave that we start with, and the second harmonic would be that you have 2 periods in one, right? So it's just when I'm talking about harmonics, what I mean are sine waves with integer multiples of that frequency. Now, this is kind of, I don't know, like super outdated example, but I like it, so I put it there. And I use it to illustrate how sounds are mixed together, because I said that many sine waves together make a sound. What does it mean? And this nice example was if you ever used a landline telephone, you heard something like this. So what these things are, they are basically sine waves that communicate between your telephone and the switching thingy, which, you know, makes connection with the other person. And it's called dual tone multi-frequency. And the way how it works is that you have your keypad over there, and each row and each column has a frequency assigned. And if you press a button on your phone, oops, I forgot to turn off the, you know, the thingy from over here. It's going to be a little bit buggy presentation. I'm sorry about it. Anyway, here's like this, right? So what happens is that you take the frequency from the row, from the column, and you play them at the same time. And you can see that on a power spectrum, right? It's 2 sine waves. And how you do that practically is you just add these sine waves together, right? So you calculate one sine wave, the other one, and you just, you know, sum them. And that's it. That's how you mix sounds, how you mix signals, right? And in this particular example, it was, used, you know, for a practical purpose, so that, you know, you cannot just whistle in a phone and then you dial something by accident. So they use these 2 frequencies that have to play at the same time. And since we have this ability to switch between the time domain and the frequency domain, it's very easy to decode which frequencies were there, right? So when I play this, you know, the signal seems kind of messy, but in the power spectrum, in the frequency domain, it's very clear which frequencies are we hearing right now. Fourier transform is it's a continuous thing, but here we are working with a digital signal. You know, it's sampled. It's just a couple of numbers. So what we have to use actually is a discrete Fourier transform, right? And the way how that works actually is that you have to take some small window of sound, right? So for instance, the one that we see over here, right? And then you take that signal and that piece of signal, and then just run, you know, fast Fourier transform on that one, and that's how you get your current power spectrum at that time, because, you know, sound changes. It's not always constant, right? It always changes. So you have to do this all the time. The problem with that is, you know, if you just cut a piece of signal at the end, it's not continuous, right? And so what would you actually see is something like, give me a second, please. Is this. You know, you would have a bunch of frequencies there that are actually not in the signal, but since we are just cutting the sine wave, you know, let me do it like that so that you can actually see better. You know, I cut it somewhere, you know, and the beginning and end, they don't align. And this misalignment, you know, the Fourier transform would interpret as, you know, it's in a signal. And that's where you get all these weird frequencies there that are not supposed to be there. So how do we get rid of them? We smooth it, you know, we can smooth it. Let me do it like this. let's go with this, right? We can use such a smoothing function, you know, so that at the end it's just going to 0, and that will basically get rid of all these frequencies because our window is then continuous, you know, and then we can just run the fast Fourier transform on our smooth signal. Okay, let's now come to, you know, how do you actually make nice sounds with a synthesizer. And what synthesizers are usually doing is that they take some sound waves that they construct mathematically, and then they modify them with some modifiers. So very basic, you know, very start of the sound synthesis is making different sound waves. Sound waves. Sine wave, you already heard, you know, it is pure tone. But there are much more interesting ones, and one of them would be this sawtooth wave. So the way how it works from this equation, I mean, looks complicated, but what it is basically, it's just a sum of several sine waves, several different harmonics of the same wave. So this is your fundamental, and then you take several harmonics of that fundamental and add them together. What you will get is a sawtooth wave. It looks, you know, if you repeat this, it will look like a sawtooth. We can also take a look at the individual harmonics like here, and you can see that, you know, this is the first one, the second, third, and so on. So there are all harmonics in there, but they are gradually decreasing their amplitude. And you can also hear it, sounds like that. And you can see all these frequencies there in a power spectrum, right? So they are all there, and they are decreasing with amplitude. That's how it sounds like. So that would be one of the most basic sounds that you hear in all sorts of music. It's used all over in different synthesizers. Another one, which is also very, very useful, is a square wave. And again, it's a sum of different harmonics, but you can see in the formula that it's actually only the odd harmonics there, you know, so first, third, and so on. Again, if you look at it like this, you can see that you have a first one, and then you have a, does it make sense? Yes, you have a third one, right? So you have a three periods per one period over here, and so on. So again, if we take a look at it, that's how it sounds, that's how you can hear it. And if I switch between them, you can see, you know, how they, you see it in the power spectrum. So this one, this guy over here is here in the sawtooth, but it's not there in a square, right? Because in the square you have only every second one. So this is that. Which is kind of cool, is that, you know, I talked about this phase, right? Like how you can change frequency with it, but the actual phase, our ear, they don't really hear it, right? I mean, you don't really know where the sine wave started. So what's kind of cool, you can like randomize it, right? You can move these sine waves. It still sounds the same, right? But it looks completely different. In the time domain, in the frequency domain, it's the same, right? Because we just move the phase. Yeah, but we don't move the frequency. That's what we hear. We hear the frequencies, right? So, I mean, that's useless. Bit of trivia, right? I just found it cool that you can do that. Anyway, another wave is a triangle wave. Again, you just have odd harmonics, but you can see they are decreasing much more rapidly. That's also why it sounds much more like a sine wave. It's kind of like a digitalized sine wave. You know, if I switch between, that's a sine wave, that's a triangle, right? That's much more subtle difference than between, you know, this and this. And that's because this, you know, the main frequency, the fundamental, is so much louder than everything else. And you can see, you know, also in this Fourier transform, how these higher harmonics are much, much quieter. You know, quieter means they are squished like this, right? Again, we can do the thing with the face. It's kind of cool. Huh. All right. So there's that. Yeah?
It looks like the Su and those triangle waves seems much difficult than sound waves because most are conventional sound waves. Yeah. Those school chips, I don't think that they could produce some sine wave.
Exactly. We will come to that. So it's a very good point.
Okay, so
depends on what, right? If you are on a computer chip, of course, it's easiest to produce the square wave, right? I mean, you just go and you just put either 1 or 0, right? You just go for the half a period, put just 1, 1, 1, 1, 0, 0, 0, 1, 1. But that's a different thing. So this is this is the mathematical expression of the what am I doing? Yeah, of the square wave. But truth to be told, if you want to actual square wave, you would have to have infinite of these harmonics. They never end, right? So that's why it's also kind of wavy here, because we didn't add enough harmonics. If we would add more, it will get more like a square wave, right? You can see it here, right? It gets, if I'm removing the harmonics, it gradually gets more and more wavy, right? So it's just the mathematical formulation, but we will see later. I mean, I always say this, but why that's important. Yep?
You have a question. So if you have a square wave, let's say it's like a completely digital square wave, it's just constructed samples. What does the membrane of the speaker do? How close can you match the square wave in what it does?
Well, it's yeah, I don't know. Very fast, right? But it, of course, it's not instant, right? It has to physically move.
So because of the momentum, it almost smooths out the square wave, even if...
It does, yeah, of course. But it does so like quickly that you usually don't hear that. So sound in computers are usually sampled at like 44,000 hertz, which is like twice as much as you can actually hear. And so it's much faster than you can detect. So it takes it some time, but it's negligible for us. But we will get to these digital ones later, right? So let's just quickly look at a couple of others which are kind of cool. So there was a triangle. This is like asymmetric triangle, you know, a super complicated formula. But, sorry, what you can do with this formula, you can actually change the slope of it, you know? So it's this little W parameter over there that we are modifying. You know, forget the formula, doesn't matter. You can look it up, right? I just want to illustrate, you know, that things can be made from sine wave. This is how it sounds like, by the way. You hear the change? So like we are now gradually getting more and more to more interesting sounds. You can also see in a power spectrum, right, what it actually does. The fundamentals stay the same. Only thing that changes are these harmonics, and that makes this change in the sound. Anyway, so this is this one, and the last one, which is basically, you know, square wave, where you change the width of it. Again, complicated formula, doesn't matter, but if you change this W parameter, this is what you will get. And it sounds like this. See, when it comes to a single line, you don't hear anything, right? Because all these harmonics, they cancel each other out. But yeah, it's also kind of cool sound. So these are like a couple of these waves that you can express with a, you know, sum of sine waves. As I said, you can express any. But these are kind of simple, right? It's just kind of, you know, harmonics which decrease in amplitude. Yeah. So that's that, and let's now get kind of to what you guys were mentioning. And it's all kind of related to anti-aliasing and aliasing. So what's aliasing in sound at all, right? How does it make sense? Let's take a look. So imagine you have this sine wave, right? Which is the changes in air pressure, which are continuous, you know, they're analog, and so you can have a perfect sine wave. What computer does, it cannot process analog signal. It has to digitalize it, which means that we would have to take samples of it. In regular intervals, we will just measure where the sine wave is. What that would do is that the computer would actually work with such a signal. You know, this is what a computer sees. It doesn't see anything else. It doesn't know that it was a sine wave. It just has this set of samples and plays that back. You know, so the membrane in the speaker would be moving. You know, it would be high, then a little bit lower, and then be 0, and so on. Right? It still does, you know, sound good enough if you make these samples, you know, frequent enough. So as I said, typically it will be like 44.1 thousand hertz or 48,000 hertz, sometimes even more. So that's what computer does. Now, let's see what happens if we are increasing the frequency of the sine wave very slowly, okay? So we are always taking the samples at the same times, right? So we cannot move it like this, but you can see what's happening to the wave that computer sees, right? It's getting really kind of rough, all the way up until here. This is where we are sampling in the half of the frequency of the sound. It's called the Nyquist frequency, and it's very important. Because if you want to reproduce any signal, you need to sample higher than that. If you sample exactly that, sometimes it works out like in this case, but imagine that you would move the phase a little bit, right? And you would end up here. So if you're sampling exactly the Nyquist frequency, you are not guaranteed anymore to be able to reconstruct the signal. So you have to sample higher. Now, let's take a look what happens further if we are increasing the frequency even more than that, beyond the Nyquist frequency. It looks like the frequency for the computer is getting lower, even though we are increasing the frequency of the sine wave. How come? Well, because we don't have enough samples, right? We are sampling here, we take 3 samples per 1.5 periods of a sine wave. And so for the computer, it looks like we actually have a, lower frequency sine wave. For the computer, there's no way to tell that this was actually higher frequency. So if you have a signal that you sample at certain sampling rate, and it has frequencies in it which are higher than the Nyquist frequency, which is half of the sampling frequency, it will reflect back into your spectrum, and that's aliasing. So once you get aliasing, you cannot get rid of it because there is no way for the, to tell from the sample signal if that was actually there or not. Let's increase it even higher because I have a button for that, so why not? So you can see if we are further increasing the frequency of the signal, the frequency of the sampled signal is getting lower all the way up until here, where we are sampling at exactly the frequency of the signal. There it doesn't even make difference if I change the phase or not. It's always going to be always the same point, so you can hear nothing. And if you increase the frequency even further, again it goes down. So it goes up and down, right? Yeah, so that's that. What can we do to fight it? Well, we can take more samples, but that's not always possible, right? So if we take enough samples so that we have at least one or more than one actually per period, we can reconstruct the signal. It's very ugly, but we can tell that it's a sine wave. So that's aliasing, and the question is, what can you do about it? And the answer is nothing. So once it happens, you cannot do anything about it. However, what you can do, you can prevent it from happening in the first place. So imagine that you would generate, as you asked, these sine waves digitally. So you just send ones, then you would send zeros, then you would send ones, then you would send zeros. What you would have infinite amount of frequencies. So it would look something like this in a frequency domain, right? They would go infinitely forever. However, you are sampling this, right? So you are just sending this one every, 44,000th of a second. So, all the frequencies above the Nyquist, they would not be represented in your signal. They would appear as aliasing. And actually, let's hear it, because that's always better than just looking at the things. So I prepared this little example where we can see here a sawtooth wave, right? Let me just switch back to this. Yeah, so we have a sawtooth wave, right? It's like this, and it's generated digitally. So we just increasing the value, and then we drop. So it has infinite harmonics in it, and this is how it sounds like when we're increasing the frequency continuously. You see that? You hear that? Like scratching. That's the aliasing. And we end up with this. I mean, it's not even in a signal. Now we are at 22,000 hertz. You shouldn't be hearing anything, but you hear aliasing. Right? This is how it's supposed to. I will play it once more time without me talking into it so we can actually hear it. So that was aliasing. This is how it would sound like without aliasing. See, it goes up until, there is still something. I mean, nothing's perfect, but you cannot hear anything, right? You couldn't hear the aliasing there. And so, going back here, so yeah, as I said, once you get aliasing, you cannot distinguish it from the signal. There is no way to remove it because you don't know which frequencies were originally there, which not. So what can you do about it? You can, well, increase the sampling rate, right? All the way, so all the frequencies, I mean, as I said, it goes forever, but since they are decreasing, at some point they are so silent, these harmonics, you can't hear them anymore. To increase the sampling rate, then you would low-pass filter it. Low-pass filtering means that you remove the higher frequencies from a signal. You can do that, no problem. Simple low-pass filter you might know as a blur, right? So that's easy. And then you can, go back to your original sampling frequency. Now you don't have any frequencies above Nyquist, and you will not have any aliasing. So this is what you might know from computer graphics as a super sampling. You can render the picture in high resolution, and then you can just like average, several points, and you will get anti-aliased picture. This averaging, that's the low-pass filter. And in sound, it will turn the waves into something like this. It will make them rounder. And so, it will actually be reflected in how the membrane moves in a speaker. Because, it cannot move instantaneously, but it kind of can move gradually. So that's one way to get rid of aliasing when you're generating these sound waves, Another way would be, does anybody of you know what FXAA is? The fast approximate anti-aliasing. You take a picture, you detect edges in it, and you blur the edges. So you can do the same thing for sound, right? You can detect edges. Edges would be discontinuities in the signal, right? So you can detect them, and then you can simply blur the signal where the edges are. You'll get the same thing. Not same, but that's kind of like cheating, right? It's fake, but it will end up in the same result, so you don't care, right? That's another way how you can work with that. And the third way how you can deal with this aliasing, which is exactly what I did in the scene that I was showing you before, you can generate the waves, mathematically, and you just stop generating them when you hit the Nyquist, right? So you just make a bunch of them, but all the frequencies that are above Nyquist, they will be removed. And they would not be generated at all, right? You just stop your for loop. You can take a look here. So you can see it's not the perfect sawtooth wave, right? When I play this again, you can notice how at some point the sawtooth wave would start losing harmonics, and they will be removed from there. Check it out. See, and we end up with a sine wave. That's actually what you hear over there. It's alias sine wave because it's at the Nyquist, exactly. But you don't care, right? It's so high that it just sounds all right. It sounds that it belongs there. You cannot hear these frequencies anyway. So if you would actually have actual sawtooth, which is that high, it actually would be just a sine wave. Your ears would only pick up the fundamental. So that's why it's okay to kind of modify this sawtooth wave like that. Anyway, let's get back to this. So yeah, I think that's it for this theory part. Now let's actually take a look at actual synthesizers. So I brought one. It's a little digital recreation of these two classical synthesizers that all of you have heard before. I wouldn't even start naming the bands that are using one of these two because it's basically all of them. They are both analog, which means that they are using electric circuitry to generate these waves and everything. Here the same company recreated it in digital, but it's much more compact, so it's much easier to show you. So that's the thing. It's a little bit squished because, as I said, nothing is perfect, and I couldn't fix this in time for this seminar. But this is the synthesizer over here, and is it bright enough? Let's say yes. Yeah, it can sound like different things. Yeah, so it has a lot of presets, but what's interesting for us are actually all these dials that are there. I can highlight them a little bit for you so you can see better what I'm doing. Let's just go through individual parts, because you can see it's split in different parts, and I will just explain what all of these parts are. Can I take this with me somewhere here? Maybe. So, This section is all about a keyboard, and it's not really interesting for synthesis. It's interesting for if you're playing on the synth. There is a button which is called hold. I can just press the button, and then I can release it, and it plays it, right? If I wouldn't do that, it would behave as you would expect, right? And then you have like a chord, which is for like people who don't know how to play music, just like me. You just press one button, and it plays a chord. It's a little bit too loud, I think. So it's good for, if you're like kind of trying to be in a band and don't know how to play music, so it's a little bit helpful. And then some other button that's not important. Then we have a arpeggio section over here, and that is a very nifty tool. Let me just, if you play a chord, that means that you play several keys at the same time. What arpeggiator does, it does an arpeggio. It means it plays individual notes like this. Let's make it. So if I press this button over here, I can just hold it. It plays it for me, It's a very useful thing in synthesizers because it allows people who really are musically untalented, just like me, to actually play music, It does it for you. It's very rhythmical, right? Because if I would try to do that, I wouldn't be that rhythmical. So that's arpeggiator over there. So you have several oscillators in this synth. An oscillator is basically a little module that generates these waves. So you can have a you can have a square wave, for instance. You can see it's not a perfect square wave because, it's analog. So it generates it with electricity, and there you cannot make a perfect square wave, but it's close enough, So that's how it looks like in this synth. It has a triangle one, the sawtooth one as well. Again, not perfect. There is this spike there. You can see the frequencies, and they kind of go down. That's the anti-aliasing, right? They didn't want to generate all of the, harmonics. So there it goes down. See? And then you have another one, which is a square wave 1 octave lower. You can play them together. Yeah, so that's the oscillator section. And you can do different things, like you can move the width of this thing, just like we saw before. And going back to the one that I skipped, it's called LFO, and that means low frequency oscillator. So what it does, it generates a triangle wave or sine wave, I don't know, whatever is said here right now, and it can change certain parameters, right? So I can, for instance, increase the rate of it, and I can change the frequency with it, right? Or a bunch of other things. But that's the, if I change the rate, it changes how fast, does it change the parameter. So that's a low frequency oscillator. Also, LFO, you will see it on every synth, right? It's always called like that. And it's very often present in synthesizers because in music or in generating sounds, it's very important that these sounds are kind of alive. They move, they change over time. Because if they are static, they are just as boring as all these sounds that I'm playing for you. It's just bzzz, it's nothing. So usually when you want to make a nice sound, you want to change something. Over time, and LFO is the best tool to do that. Okay, now we come to the next part. We start maybe with this one, and that says, it's a little bit misaligned. I'm sorry about that. It says VCF, which stands for voltage controlled filter, and that's your filter. It's a low pass filter. What it does is, let's make this stop. What it does, it filters the high frequencies, right? So we can do this, and you can see in the power spectrum that you are removing the frequencies from the top. And you can also see in the time domain what happens. It's like the signal gets kind of blurred, and you can see it even better if we show the signal as this pressure. I told you that that's not very common or useful way to do it, but in this particular case, I think it's pretty useful to have it like that. So let's try if we can do that. Yeah. So that's how it looks like, right? It's simply mapped. If it's lower, then it's darker. If it's higher, it's brighter. That's it, right? Simple mapping. And look what happens when I'm decreasing the frequency, the cutoff frequency of the filter. So from which frequency on everything will be cut. Yes, exactly, you can, and I will show you. But first, watch this. See what happens when I'm decreasing the filter? Oop, it blurs, because it is essentially a blur, right? And yes, you can control the cutoff with a LFO, right? There is this slider over here for that. And yeah. See, it goes up and down. So that's one useful thing to use the LFO for. Yeah, another section over here that I also skipped was another filter. It's a high-pass filter. So what it does is it cuts from the bottom. And watch the time domain as well. It basically detects edges, right? Because that's what a high-pass filter is, right? You throw away everything, you just skip these big changes. Big changes means higher frequencies, right? Because you have to go very fast from top to bottom, Fast means high frequency. So that's what your high-pass filter does. Let's hear it on this one. See, it removes this, it just keeps the buzz. That one you cannot control with LFO, unfortunately, on this particular synth. It's always kind of like a trade-off between how many knobs and things, controls you have, and what's actually useful musically. And so, this high-pass filter, yeah, it often is, because basically, as I said before, when you are combining sounds, here you are combining many sounds together, and they're all edits together, right? And so if you have a lot of low frequencies in there, which you don't even hear, they will add up and they will make your signal very high. And you can't go infinitely high, right? At some point it will clip. And we will also look at what clipping does to a signal, but it's not good. That's a spoiler alert. Another section over here is an amplifier. And again, it's a VCA, means voltage control amplifier. Voltage control means exactly that you can control it with some other signal, like LFO, right? So, yeah, I mean, I already showed you, right? That was basically, oh no, I didn't. It's very counterintuitively, it's controlled with a control at the oscillator section in here, but doesn't matter. Point is, no, that doesn't, no, see, I was lying, not at all. No, you cannot do it on this synth, sorry. That was my mistake. You can change the level though. Only with your finger though. So that's an amplifier. Usually on synth you would be able to like plug some cable in there which goes from LFO and then change it gradually. Not on this one, unfortunately. And the last section, that's musically I think the most important one. It's called envelope. And it's so important that I even put a separate camera just for that one. Yeah. And of course it's out of place again, so we'll just move it here. Anyway, what the envelope does, it's a signal generator, which generates a signal over time. And let's see if we can actually see that signal. Looks kind of like this. It has 4 parameters, and these 4 parameters are controlling the curve. The first one is a attack, and that is the duration of how fast does the signal go from 0 to all the way to the top. So it's this first section. It's called attack. The second one is called decay, which is how fast does it take for this curve to go from all the way to the top to certain value, predefined value. And the third slider is that value, So how low does it get after the decay? So you have attack, which is the first part. You have decay, which is the second part. Then you have a, oh man, I'm blanking on this one. Sustain, thank you. You have a sustain, which is the level, the amplitude of it. So it's not the duration. And this duration, I should maybe have said before what it does. But anyway, the last one is the release, and that's a duration of how long does it take to the signal to go from the sustain all the way down. Now, this is most commonly used to modify the amplitude of the generated signal, so the volume of it. So this is how the volume changes over time. It starts at 0, it continuously goes all the way up as much as it can, then it decays to the sustain value, and that sustain value will be held while you're holding the button down. And then when you release the button, it will for some time sound and go all the way down. Listen to this. If I basically make it like that, you know? Sounds like you would imagine. Now let's add some attack to it. Oh, that was too little. Do you hear the difference? It goes from, instead of brr, it goes like, right? So that's attack. The second section, the decay, only works when you decrease the sustain, right? So let's put it like this. It will go, let's just forget about the attack for a bit, okay? So it will start all the way to the top, but it will decrease to a certain lower level. Don't really hear that, but if you make it more drastic, even more drastic, hear that at the beginning? That's because it starts all the way to the top and then decreases. That's that. And if you make it longer, you know, you can also see it in the time domain over there, right? Maybe I turn this off so it looks better. Actually doesn't matter. So this is the decay, right? And the sustain, while I'm holding the key down, the sustain would be the volume of it, so I can also change it. See what happens to the signal? If I go with the sustain all the way down, it just goes to the silence. If I go all the way up, it goes back there. And then, you know, the sound always just abruptly ends, because we don't have any release. If I put some release in there, I release, continuously goes, fades away. So this is, I think, musically the most important thing here, because synthesizers, they are originally made to reproduce sounds of real instruments. And so real instruments never sound like this, right? That you cannot play this on a guitar. All these physical things that vibrate, like strings and pieces of wood, they would have some sort of, you know, duration until, you know, like if you hit the drum, for instance, you know, first it's super loud, but then gets quieter, right? And so, you know, this is not an example of a drum, but it can sound much more musical when you use envelope on your amplitude. You can also use the envelope on your filter, for instance, right? So let's turn this off, and let's just use it on a filter instead. Let's do that. Okay. Do you hear how the sound changes? It's like the nature of the sound changes over time. It's like, yeah, whatever. The last section over there, I mean, again, it's just a little gimmick of this particular synth. A lot of synth have that as well. It is a sequencer, which means you can pre-program it. You can, these buttons, they are notes that you can like pre-program which notes does you play, and then you just go start. You know, and then it does whatever. You can move these things, and it plays whatever notes are programmed there, right? I kind of forgot to talk to you about this kind of guy, which is part of the filter, and it's pretty actually useful. It's called resonance, and it actually amplifies the frequencies around your cutoff frequency of a filter. So let's go back to the power spectrum to quickly show you that. Let's say that I play sound like this, and I have a low pass filter, right? So you can see approximately where is the cutoff frequency, where there's nothing above it. And the resonance is amplifying those frequencies in that small range around there, so I can go like. Right, that if I'm moving the cutoff, this frequency range, it's also moving with it. What a lot of synthesizers do, which is also pretty cool, they are changing the cutoff frequency based on which note do I play. So if I play this one, the cutoff would be somewhere else if I play this one. Now, that's particularly cool because what you can do, you can turn off your oscillators, so you hear nothing, but then you turn up your resonance, which will then pick up the noise naturally generated by the synth. And if you turn the resonance all the way up, it will amplify those frequencies around your cutoff, and you will hear it as a sine wave. And since the cutoff changes with your note, you can play your filter. And I'm saying this because this is one way how to generate a sine wave. You can use a filter, you can use a resonance frequency of a filter, and then you can play it, which is kind of cool. Yeah, so that's synthesizers. That's my little demo here. Yeah, I think now we can get to the coding part really quickly, no? And go to the common tab. As I said before, we have this one function called song where we can code something. And I already made some of these oscillators for you. They are, these two, saw and square, they are a little bit anti-aliased with whatever algorithm. I will not get into details of that now because we're kind of short on time already. But they are there. And the way how they work, it's basically a function where first parameter is the phase, the second is x, that's basically the time, right? It's your x coordinate. And then it's a frequency. So if I would go here, and I have to return from this function a vec2. I asked before, but I ask again, is there anybody who never worked with like GLSL? Okay, cool. So it's just GLSL, right? So it returns a vec2, and the first element is the right ear, the other one is the left. And so, yeah, if you return the same number, then it will just play the same thing in both ears. So here we are playing this sinus. But what we can do instead, we can play I don't know, saw. Right? And the saw has the parameters, the phase, the time, and the frequency. So we'll put a time in there, and do you have to multiply it by 2 pi? No, you don't, because it doesn't use sinus. So you say, let's say, we say 0 phase, doesn't matter now. T is the time in seconds, and the F is the frequency in hertz. So if I do this, and then I hit compile over here, it gives me a sawtooth. As I told you before, you have to hit this reset if you want to hear it. And then, you have to hit play and pause to pause it, actually. It's somehow paused at the beginning, I don't know why. So that's how you make a sawtooth. And it's kind of boring, right? It's just, not even boring, it's annoying. So as I said, musically, the most important thing is the envelope. So let's put an envelope around it. Let's decrease the amplitude. And so now we are basically making a math function, that calculates something. The very useful tool for that is, all these graph plotters. We can see how the function works. Like a good one from the same author as a shader toy is called Graph Toy. I don't know if you know about it, but it's pretty useful. And yeah, it just plots functions, right? You can turn them off like this. And so let's try to make an envelope, so something that would decrease gradually. Because, if you plug a guitar, for instance, if you hit a drum, it always starts loud and then continues to decrease. So let's find a function that goes kind of like this. A good example would be this exponential function, right? If you go like that. It's just wrong way around, right? So I just put minus in front of it. I don't know, can you see this? Is it too small or is it okay? Let's put it like this. That's a yes, if I ever heard one. So now we have kind of, you know, decreasing function. It's, yeah, if you know, the nice property of it is that it starts at 1. So generally these signals, you know, that we are generating, we want to go from 1 to -1. If it's 0, it's in the middle, 1 is all the way to the top, -1 is all the way to the bottom. So this is perfect for us, starts at 1 and decays to 0. So let's just take this function and let's multiply our sawtooth with it. Let's see what happens. And x, of course, is called t over here. See, it decays. It decays over time. Now we want to make it much faster, right? Because this is kind of slow. So how to make it faster? We have to squish it like this. So how do you squish it like this? Well, you multiply x by something, right? I don't know, 200, or let's start with something less drastic, like 30. Why does it disappear now? Yeah. See, if I multiply it by some number, it gets squished like this. So it will be much shorter because, you know, x is time, right? So if I multiply it by 30, it will be 30 times shorter. Let's see how that sounds like, okay? Multiply here t by 30. You always have to put dot, right? So it has to be floats. Just a little thing, you know, this WebGL, I don't know if you work with WebGL, but it doesn't tolerate just 30, right? It needs to be 30 dot, which means 30, 0. Anyway, if you compile that and reset, see? Much shorter. Let's try to make a kick drum. So we already have a good base, right? Kick drum is like very short, you know, and this is very short. It's just kind of very high frequency, you know? So let's just try to make the frequency lower. I know what's gonna happen. Let's put like, I don't know, 100. Recompile. All right, doesn't sound like a kick drum, but we are getting somewhere. The thing about the kick drum is that like sawtooth wouldn't be like very, you know, representative of what it sounds like. You know, if you think about it, if you hit a drum, it's a membrane, it kind of waves like this. So we should rather use a sine wave. I will use a triangle in here because basically it's the same thing. You cannot really hear it if it's so short. So let's see what happens if I just change this to triangle. I think triangle has different parameters though. It doesn't have a phase in here and doesn't have the frequency in here. That's a pity. Yeah, I should have made it the same. I didn't. So what are we going to do? Well, you simply multiply the t by 2 pi and by frequency. You know, 2 pi because I'm using the same thing as a sinus here. Is this clear why I'm multiplying this by 2 pi right now? I take that as a yes. And then you multiply by frequency, you know, and then you just have one parameter, that's time, right? And see what happens. You know, you have a triangle. Okay, it's pretty silent. Can we make it louder somehow? Well, I can't make it louder, so what I do, I just multiply this by like 10. There we go. Okay, so now what happens with a drum though, when you hit it, the membrane vibrates at some frequency, but as it slows down, the frequency will be lowering down. So what we can use here is a frequency modulation. We can put, you know, an envelope to the frequency so the frequency gets lower over time. And we can do that by taking this thing over here, and we can put it in the frequency over here, you know, so the frequency gets down as well. I have no idea what's going to happen, to be honest. Let's just try. You know, this is a lot of experimentation. There. It's kind of like a drum, you know, and then we would tweak the parameters forever. But since we don't have time, let's call this, you know, that's our drum. Now, it's not very interesting to just like press this button all the time, right? You would like to hear the drum in some pattern, right? So how do we do that? Well, as I said, you know, this is kind of like a continuous signal that is generated. At the beginning of it, we have this drum, and then we have nothing, right? So how about we take this time, and we, you know, do the modulo on it so that it repeats, you know? So it doesn't go from 1 to 2, 3, 4, 5, just goes like from 0 to 1, from 0 to 1, from 0 to 1, and so on. So what we can simply do is we can modulo the time. And since we have the time here several times, I think the easiest way to do would be to make a function for this drum over here So we just take this and put it in a separate function, okay? We call it kick. As a kick drum, it just takes T as a parameter. Oop. And returns whatever we had there before. Let's just see if it works. So I just put here kick, and I put it T as a time parameter. Yeah, it's the same thing as before. Now, instead of T, let's put a modulo there. Right, and let's put 1. So it will now hit the kick drum every second, hopefully. I don't know, I suck at math. There we go. Let's make this a little bit faster maybe, but you know, like, just so that we don't get lost in too many numbers and stuff, let's actually calculate the BPM of the song. So BPM is beats per minute. It's how many beats do you have there per minute. And yeah, that's usually how, you know, speed of the song or the tempo of the song is like defined in at least electronic music. And let's just say, I don't know, like, I'm just looking up how much did I use before. Okay, let's make something pretty fast. 180, let's say, you know, that's really fast. And then let's calculate, okay, so we have to transform this now into our seconds, right? So let's calculate beats per second, which will be beats per minute divided by 60, right? And so you have beats per second. And then what we want to really calculate is the duration of, you know, one beat, right? And so that we will simply do by 1 divided by BPS, right? And so now we have a duration of a beat. And what we can, that's completely wrong though. Okay, so let's just call the beat, which are like 4, you know, ticks. That will be 1 beat, okay? So we will just multiply this by 4 because, yeah, that's how this one software that I'm using is working, and I'm used to that. So yeah, so we have a duration of a beat here, so instead of this 1 second, we put it over here, and it should be now a little bit faster. It's not, it's slower. I screwed up. Why did I screw up? Who can tell me? Bar, that's a cool name. So if I put this to 1, what happens? Now this is 180 per minute, right? So we have a kick drum, you know, like, let's try to make this basic rhythm, something. So for that we need a snare drum, right? So something a little bit brighter, a little bit higher. That's those drums with a mesh in it, you know, like when you hit it, there's this metal thingy. And I don't know, let's try to make a new function. Let's just copy this kick. Let's just start with that one. And let's just call it snare. And let's put it here. And I'll just, you know, I'll cheat and I'll take a look what I did before. Okay, so for the snare, it has this metal mesh in it, right? And when you hit a metal mesh, it's like a lot of frequencies, and so we will simulate it with noise. Noise, I already put a function here that generates noise. It's just random values, you know? Let's quickly hear how it sounds like, because I don't remember, frankly. So when I put noise here and I just put T, let's see if it sounds like noise. Oh, it sounds like nothing. Why is that? Maybe I have to multiply it by something? No, I don't see anything anymore. Maybe I have to multiply this T by something. Oh, we are getting somewhere. All right, okay. Yeah. It's not perfect, you know, it's just like very, very simple, some simple formula over here, which I copied from the internet. But it kind of sounds like a noise, and we'll just not need very short amount of it, right? So we just multiply it by some number. Let's say this one. It's very repetitive, but doesn't matter, right? It kind of sounds like noise, you know, and kind of you can imagine that it's a little bit metallic, right? It's kind of harsh and weird. So we will use that for the noise. And we will add that to our snare sound. So let's back to the snare. It's now the same as a kick, right? Yeah. Okay, and we will just add some noise to it. Let's see what happens. Of course, we want to, you know, envelope our noise as well, so it doesn't sound all the time, but just for a very short period of time. And see, it's different. It sounds like you hit something kind of random, like metal mesh. And so let's do now, you know, a kick, a snare, a kick, a snare, a kick. So how do we do that? Well, again, we can add them together, right? So as we have a snare here, we can just add kick to it. But they will sound at the same time. So let's just add them together and see what happens. Yeah, they sound together. So we'll just offset one of them, you know, half of the bar. You know, and our bar, which I call beat here, let's call it beat, you know, so that we are consistent. You know, we just add it to the time. We just offset the time by half of the beat, right? So what happened, it will be first snare, then kick. Well, let's put kick first. I don't know. Doesn't matter, but I like it better like that. Hear the difference? And now you have like a very simple beat. Now, let's add hi-hat, you know, like usually when they go on drums, they go on so let's add hi-hat. Hi-hat, again, it's just a piece of metal, right? When you hit it, it's very short, so essentially we can just use the snare, but make it shorter. Let's see what happens. So let's make another function called hi-hat. And yeah, let's just make it shorter. As you remember, these exponential envelopes, right? If you multiply this by a higher number, it will be shorter. So let's just put 300. I don't care. Let's hear how it sounds like. Let's just add it again to the signal. And let's make it, you know, twice as fast, you know, so that it goes on every kick and every snare. So how do we do that? Well, we will either multiply this by 2 or divide. I don't know. I don't want to think, so we'll just try. Yeah, it's cool, but we cannot really hear it because it kind of overlaps with our drums, right? So let's offset it just, you know, 1/2 of, you know, so it's in between the kick and the snare. And actually, while we edit, let's just make it, you know, always at the kick, then in between, then on the snare, then in between, then on the kick, you know, so we'll just multiply it by 4. No, maybe I should divide it by 4. I don't know. Let's like first do it, and when it works, I will explain to you why it does work. No, yeah, it works like this. And why do you have to divide it by 4 and not multiply? Yeah, it doesn't matter. It works like this, right? And that's it, right? So yeah, we won't know why. Because it's a duration, right? Beat is the duration. So we want to have a duration of this whole, you know, thing 4 times as shorter. And you know, this is the second parameter of the modulo. So we are doing the modulo 4 times more often, right? That's why divided by 4, not multiply. This is how I always program, you know? I just guess, then it doesn't work, then I do the other choice, that works, and then I try to figure out why does it work. You shouldn't do it like that, but I wouldn't blame you if you do, because I do, and yeah. So we have a simple beat, right? Now let's add some, you know, sounds to it. We already have a couple of oscillators here. We have this, you know, this sawtooth, this square, triangle. So let's start with a saw, you know, it's kind of a classic. So let's just add a sawtooth. The sawtooth, again, has this phase as the first parameter. Let's just keep it at 0. And then it has the time, and then it has the frequency. So I always keep putting 440, and that's because that's like this A, you know, this guy. That was an A. That's an A, right? That sounded the same, right? Yeah, so we have like an A. Now, let's see what we can do with it, because the saw on its own, it's kind of boring. By the way, I made these defines over here, and these are the individual tones on a, on a keyboard, and there are these numbers here. These are MIDI codes, doesn't matter. The point is you have a function here which turns that into a frequency. So here, by the way, that's a function, right? We start at the middle A, and it's an exponential function, So like if you play A over here, and then A 1 octave higher, it's twice the frequency. Doesn't matter too much. Point is that you have this function here. So if you want to play A, you don't have to write 440 here. You can just use this function and say, let's say A4. These numbers, A3, A4, that's like which octave that is. So let's just say A4 over there, and we will get the same thing, I think. Yeah, let's say yes. Now, what can we do with it? Like one cool thing, which is super easy to make, is to play two saw waves at the same time. And the way how it sounds, how do you think it will sound? The same is the answer, right? Just louder, because you just add them together. So it will be the same thing, so that's kind of boring, right? However, what you can do, you can change their frequencies a little bit, You can detune them from each other. So let's just do that. Let's just detune, this one by, I don't know, 1 hertz, and this one with plus 1 hertz. And then they will sound like this. Hear the difference? It's like, wait, let me do it like this. This is just 1. And this is both of them. Well, no, that wasn't, because I should compile it first. This is just 1. Kind of boring. And if you put 2 of them, kind of cool, right? All right, so the thing is that, as I said, we should change things over time to make them interesting. So the easiest way will be with the LFO. So let's make an LFO. Let's call it LFO, and let's just make a sine wave that goes very slowly. Let's say, yeah. This would be 1 time a second, right? Because, yeah, it's just time in seconds times 2 pi, so 1 time a second, you have LFO. Let's see if it works. Let's multiply this whole thing by our LFO. Let's see what happens. It goes up and down 1 a second. So that's too much. Let's make it 10 times slower, right? Cool. Now, let's just remove these drums for a bit because they are kind of in a way. Yeah, that's nice and all, but also kind of, I don't know, doesn't work so much. So let's use this LFO for something better. How about we can try this detuning thing with the LFO? Or, as I mentioned before, you can just change the phase with a sine wave, and it will change the frequency as well, right? So how about we take this phase thing and put an LFO in there? Let's see what happens. I have no idea. It does something. Let's see what happens if I modify a little bit more. Now you just go -1 plus 1. How about we go -10 plus 10? Sounds the same to me. How about if I do 100? I have no idea what I'm doing, I think the problem is that it goes too slow. Let's make it faster. Let's see what happens then. Okay, now it does something. We can, play different note on different beat. So let's just define an array of notes. Let's put 4 notes. Hey Martin, give me 4 notes that sound good, one after another. Give me a
C, E, G, and then another C.
C, E, G.
And then another C, 1 octave apart.
Alright, so let's make it like 4, 3, 3, 3, and 4. So we have 4 notes, right? And let's now exchange them so it doesn't play A4 all the time, but it plays one of these. So how do we do that? Well, we need the number 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3 every beat, right? So how do we do that? Well, let's take a modulo of time, which is, this will go from 0 to 1 in 1 beat, right? We want to go from 0 to 3 in 1 beat, so we just multiply by 3. And we want integer, so we floor it, right? Is it clear? I take it as a yes. So, this should go now from 0 to 3. Did I make a mistake there?
Make it integer.
Good call. As I said, I have no idea. Let's just test it, right? Let's see what happens. And, we have to put it in the second one because we have two sawtools there. So let's also play it in this one. Okay, that works. Let's see what happens. I have no idea. We have melody. It's really harsh, right? Let's make it a little bit slower. So how to make it slower? Well, beat duration, right? Divided by 2 will be twice as slow, right? And again, you have to do this. Why doesn't it work? Because, I don't know. I do know. Because now, wait, I don't know. Let me think of it. No, come on, you guys, you think. What's wrong with this? Who knows? Well, I know. We want this guy to go from 0 to 3. And so, this, whatever number that is, would be, we make a modulo of that. So, if we want to have this number to go from 0 to 1, we have to divide it by that, And now this thing will be between 0 and 1, right? I think so. And then if you multiply by 3, you get 0 to 3, So you get 0, 1, 2, 3, 0, 1, 2, 3, and so on. Let's try it. Let's see what happens if I put it like this. Yeah, and obviously it's times, not divided, right? Because we want to have it slower, right? So duration times 2 would be longer duration, so it would be slower. So, yeah. Split second, just basically not at all. So we actually want to go up until 4, not 3. Because,
It's 4 in the index anyways, so it will be 3 and...
Exactly, then it cuts back to 0. So it was supposed to be 4, not 3. Yeah, anyway, so now we have that. Let's just, I don't know. Let's put some baseline to it or something, no? So we will make this a little bit more silent by, multiplying it by some number. I don't know, like this. And let's put our beat back to it, right? Let's see if it fits. Let's make this even slower, no? Like 4 times. Anyway, let's try to put some bass to it. I screwed up something, so what did I screw up here? You know what? Since we are running kind of out of time, we just forget that I did that. We just go with this for now. So basically, something on lower, right? So let's use, I don't know, triangle or something. Let's use the square. We don't use the square yet. And we need to make it lower, right? So let's just start with playing, I think square is the same parameters again. So we have phase, time, and frequency, and then we have a PW, which is pulse width, how wide it is. So let's just put no phase, let's put the T as a time, and then the same note, which is this. And then I think the pulse width goes from 0 to 1, if it's 0.5, it's in the middle. So let's start with that. Let's see what happens if I just do this, but if I divide the note by 2, as I told you, if you play a note and then you want to have 1 octave higher, it's twice as much frequency. The same way the other way, right? If you want to have a 1 octave lower, you just divide it by 2. So if I do this over here, I will have 1 frequency lower square wave playing together with. It's there, it's like very loud and harsh, and so let's just make again an array for baseline. So how about we just start with something simple? We just go like C2, actually, yeah, I was here multiplying by 0.5, but y, I can just specify the notes lower, right? So let's just say, I don't know, like C and like, I don't know.
C again.
Alright, C again.
C again.
We're making techno, okay.
Don't E or G there.
How about we like, I don't know, like. Okay, how about we go like. Okay, let's do that now. I don't know, whatever. So we would go like A3, C2, C2, yeah, whatever. B3, C2, C3, C2. How many is this? 8? 1, 2, 3, 4, 5, 6. And then, so what can I do? So let's just repeat this a couple of times. I don't know, let's not make it complicated. Let's just make this again. And is this 16 now? Oops. I'm missing 2 more, so let's just make it 1 more. I don't know. Let's just, we will hear how it sounds like. If it sounds stupid, then we will just change it. So we have 16 notes for our bass line. And yeah, so let's just remove this for a bit so it doesn't get in the way. Let's just play the bass line. And so what do we need? We need to change these notes to bass, right? So we have a different array now. And we want to go from 0 to 16, So like this. And if I would play it now, there is a syntax error because there is a plus, which I forgot. There's a stupid part in the middle somewhere, apparently, but let's just forget it, let's just keep going. You can tweak this later, you can play with this yourself. But what we want to do, we don't want to have this computer sound, right? We want to make it a little bit more musical. So let's put an envelope, As I said, this is the easiest thing to do to make the notes more musical. So let's take our square and let's multiply it again by such an envelope that we use in a hi-hat, for instance, right? So let's put it over here and let's see how it sounds like. Again, we have to make appropriate time. Here we just use T, but we cannot just use T. We have to use whatever we're using over here. So we have twice the beat, and then we make 16 notes in these 2 beats, right? So it's 8 beats, 8 notes per beat, right? So how do we do 8 notes per beat? Well, we do modulo, beat, and then divided by 8. Everybody understand why we are dividing it by 8? Let's wait to see if it works, then we will actually explain it, okay? It's a little bit too short, right? It's as short as the hi-hat. So let's change it to make it a little bit, okay? Sounds all right to me. Let's see what will happen if you make it even shorter, longer. It sounds all right, no? Let's make it 1 octave lower. Make it faster. Nah, I like it better like this. All right, let's make it a little bit silenter, a little bit quieter. That's too much. And let's put our beat back to it. There we go. Let's add these sawtooths. It's probably not going to fit together, right? But let's try anyway. Let's see what happens. I just, add them together. No, doesn't. I mean, it sounds like programmer music, no? Like music made by a programmer. Anyway, bless you. If I hit play, we can see that I always forget to hit play, but we have something. Okay, let's see what else can we do. I don't know. Let's just remove this thing for a while. That's doesn't really fit so much. But like, how about we try to add some melody to it? We have a bass line. That's pretty. I would say that's pretty solid. Let's just add some melody, some high notes on top of that, so that we have full range. So again, how do we do that? We start with making an array of our melody. Let's make, I don't know, who wants to tell me? I don't know. Like, I don't know, like we go like, no, I don't know, whatever, right? So it's like, let's start with that, right? So that was like, whatever, I will see later how long it's going to be. So I'll just keep it like this for now. And bass line is regular. It's just the melody, we want to have some spaces in between. So let's make 0 a space. I already put it in here, in this function over there. If you enter 0, it will just return 0. So you have 0 frequency, so you just multiply whatever you pushing there to 0, so it will sound like nothing. So we can just use 0 in our array as a pause. So what did I do there? Like, so let's say A4 space A4 space. And then, like, what's before A? Like, seriously, what's before A? I have no idea. Huh? Thank you. G4, and then again A4. So we have 1, 2, 3, 4, 5, 6, and then we just put 2 spaces in there, okay? So we have 8. Do we have 1, 2, 3, 4, 5, 6, 7, 8? Okay, so we have 8, and we will let that play over our bass. So let's use this saw again. Let's actually use both saws. I think it sounds pretty cool. So let's just copy this. And we will just play with the envelopes a little bit to make it nicer, right, for the melody. So here we use our melody in both. I will, for now, put it like that so that they are aligned, so we are putting the same thing in each. Yeah, and so, again, we have 2 beats over which our bass line goes, and we have like 8 notes, and let's make that in 1 beat. I don't know, so let's just put this here for now, and we want to go from 0 to 8. Okay, so we have 8 notes in there, and let's see what happens if we do this. Exactly, you're right. We're missing the plus. That doesn't sound right, does it? Okay, let's find a problem here. Just we'll remove this real quick. I have no clue what's going on. Maybe this is just too drastic, right? Yeah, it was just the LFO was too drastic. So it was changing the phase so much that it was actually bleeding to next note. Okay, so we have. So let's try the envelope again, right? To make it a little bit more musical. Let's just multiply these 2 things. Let's close them in a brackets and multiply it by our envelope. I will again borrow it here from the hi-hat. And let's see what it does. Way too short. And of course, yeah, let's borrow it from here actually. And we go. Let's think for a second. So we have 1 beat and we have 8 notes. So this should be correct, yes. So what happens if I do it shorter? Nah, it's too short, right? Like this? Yeah. Let's add the beat. See, and now it's kind of like weird, right? And that's because I think our signal is now too much. And it's actually hitting our -1, +1, and it's clipping. So we just make it all, less. I don't know how much. We will experiment. So let's just multiply all of these by 0.2 for now. If I multiply all of them separately, I have basically like a mix pult. I can just change these numbers and change the loudness of all the channels. Yeah, it's better. It's too silent, I know. I mean, at the beginning I just multiplied by huge numbers so we can hear something. I don't know if I can make it any louder. It's a mystery to me. Anyway, let's just go with this for now, and let's just make like a, kick a little bit huger, like. And this can go a little bit up. Whatever, and let's add our bass line to it now. It's doing something, whatever. You guys say something. You ask some questions or something. How about it? How about we do a question round? Who has a question? Who want to say something or ask something?
I'd like to ask about the volume.
Mm-hmm.
Is it just how I'm picking, or because I have like the small speakers and each one, it's about, what is it about the volume?
Yeah, so when we are talking about a signal, right? So our signal always goes from -1 to 1. And so that's basically the level that the computer is outputting, and then it goes into, usually here it goes into the amplifier, to the speakers. So the volume is modified on several places along the way, right? And so, yeah, if you have bigger speakers, bigger amplifier, it will be louder, of course, because inside of a speaker you have a membrane that goes back and forth, right? And if you have a bigger speaker, it can go more, it can push more air. So +1, -1, if you go sine wave all the way from the top to bottom, would of course sound louder on a bigger speaker than on a smaller speaker. Yeah, but for the computer it will be the same signal, but depends what you hook to the computer, how it's going to sound in the end.
So it's about the volume of air which is affected by the...
Yes, exactly. It's about the changes of pressure, right? The higher change of pressure in your ear would be perceived as louder. And
Yes, higher pressure is, volume is higher than pressure.
no, yes, I mean, no, the volume is the difference between the highest and lowest pressure, right? So if we go back to this real quick, right? If you have, the volume here is the difference between the peaks and the valleys, right? So if you have higher, it's just measuring the pressure, right? So if you have higher pressure and then lower pressure, and that repeats, it will be louder, right? And that's just physical, how do you make this sound? If you use bigger speakers, it will be louder, but the computer will be outputting the same thing, same signal, right? Low frequencies. So how do we write a high-pass filter? There are different ways. Very easy way would be, to low-pass filter it and then subtract that signal from your original one. Then you have a high-pass filter, right? So that's like a kind of crude, quick way how to do it. In the other way, it's the same way how you do the edge detection in images or emboss filter, right? So you just do the convolution, right, with certain coefficients. And if these coefficients would be for the blur, they would be in the middle, they will be high, and then they will be getting low, like Gaussian kernel, right? So yes, you can do it I'm thinking.
How do you view a window of music?
You would have to have some memory, right? So you'd have to have some array where you would store a couple of frames. I mean, here we are pre-generating everything, right? So you don't have to actually have, let's go back to the code quickly.
Well, you actually could generate previous track and next track, so you can generate your window.
Exactly. That's what you would do, right? So here we have this function which creates our song, right? So what you would do, you would take this whole function, so let's call it song0. I'm absolutely sure that I will not be able to do this right now on the spot, but let's just, theoretically, how would you go about doing that, okay? So the song is basically, or song0 is your function that generates your song, that gives you the amplitude in certain time, right? In time t. Forget about this, it's not important right now. So here, if you would just return song0, that just plays, whatever you made. So what you could do would be something like this, times W0 plus song minus S times, I will explain after I finish typing, okay? And let's just make 4 of those, let's say. Yeah, so like this, like this, like this. And S is duration of one sample, right? So that would be 1 second divided by 44,000, which is the sampling rate we are using here, okay? So, and yeah, this of course 2 and 3. So W0, 1, 2, and 3 are your coefficients for your filter, and you just do a convolution essentially. For each sample, you do a convolution of the length of 4 of the 4 previous samples, and that's your filter. Now, if I would make If I would make all W0, 1, 2, and 3 same, it should be a low-pass filter, right? Because it's just a box blur. Let's just, for the fun of it, try if it works. So we would, normally we would put average, right? So we will make them, but we can make them any value that is the same, and then we have a box filter, right? But let's just make them like this, because if they add up to more than 1, your volume would change, right? So if you make them add up to 1, the volume stays the same, and this should be now the same thing that we had before, but low-pass filtered. It's going to be embarrassing if it doesn't work. Oh yeah, because there is this thing. Like before, I also wrote the oversampling thing. I will then give you a code of the, there's a little bit more things there. You can take a look at it. And what's, yeah, this plus. Okay, there we go. It sounds the same. How about we make this a little bit? Do you hear it? So I'm basically just, I'm cheating here, right? I'm not making a longer kernel, I'm just spacing it away, right? But it's okay, for such a... Exactly. But yeah, you heard it, right? And so the high-pass filter would be basically your signal minus this, right? So let's just try if that works. This is this kind of like approximation of that. So let's just put this in a variable, low pass, and then we would return song 0 at the time of t minus low pass, right? Do you hear it? If I just return the song? Do you hear the high end, the low end? And if you think about it, right? You take a signal, you subtract the low pass filtered one, you just get left with a higher frequency. You can also see it in the waveform. It's really spiky, right? And if I just do this, it's more full. Yeah, so any other questions? All right, you guys, so this is like, my preparation for this workshop was that I wrote this shader, right? So I made such a song. So it's basically the things that we were talking about. There is this oversampling code over here. So you can take a look at it if you want. You can play around with it later. I will put this URL here again, so big, so you can type it in your thing, and then you can if you want to play around. So it's CDT, double case, SD, and lowercase l.
So actually, the question. So if this one were like a little part, like a beginning, intro, bridge, something, what do you do? What's that between the bars?
So I would do several of these functions, song 0, song 1, song 3, song whatever. And then, I would take, let's say one part takes, 64 beats, and so then I would do modulo 64, like beat time 64. And then, if it's 0, then play song 0, So I would make a if else or switch statement, But you wouldn't write music like this, right? That's unpractical, right? We are just doing it in a shader toy because it's easiest to understand how these mathematics work behind it, but you wouldn't write music. I mean, some people do, right? Let me show you this one. That was actually pretty crazy. And again, it's definitely cool to see a source code of it and try to understand it, modify it. I don't know who wrote it. I just randomly found it. Shader toy sounds acid, I think. Some people, I don't know nothing about this. I'm just here talking to you about it, but some people are crazy, Somebody made this. There you have a nice filter implementation with the resonance. Here. So if you just put this in a Google, you will find it, right? And then, see, he adds different sections as well. You can see how he did that in the code, right? It's pretty simple, right? It's 200 lines. You have also nice kick there, right? So it's pretty cool. Yeah, exactly. I mean, the shader toy is made by a dude from a demo scene, right? So it's all kind of oriented that way. All right. If there are no more questions, I have one last slide, and that is thank you.